In this lesson, we are going to develop another method to determine whether a given series converges or diverges. Today, our method will involve comparing a given series to a series that we know converges or diverges. Often, the most common kinds of series we're going to compare things to are p-series. Remember that a p-series is a series of the form sum from n equals 1 to infinity 1 over n to the p. And this kind of series converges so long as p is bigger than 1, and it diverges if p is greater than 0 but less than or equal to 1. And another series we will often compare things to is a geometric series. And recall that this series, that's r, so a times r to the n, this converges if the absolute value of r is in between 0 and 1, and it diverges if the absolute value of r is greater than 1. So first, do you think that the series, so the sum from n equals 1 to infinity of 1 over 2 to the n plus 1 should converge or diverge? So what I would say is this looks a lot like the sum from n equals 1 to infinity of 1 over 2 to the n. And that series converges because it's a geometric series with r equal to 1/2. And actually you can prove that the terms of this series are actually smaller than the terms of that series, and here's how you would show that. So 2 to the n plus 1 is certainly, sorry, not 2 to the n plus 1, 2 to the n, and then plus 1 is certainly bigger than 2 to the n. And then if we reciprocate both sides, 1 over 2 to the n plus 1 is going to be less than 1 over 2 to the n. You can think about how 7 is bigger than 5, but 1/7 is less than 1/5. A bigger denominator makes a smaller fraction, so that's why that inequality flips. Now, one could sort of assume or surmise that because this series converges and the terms of the other series are smaller than the terms of the series that we know converges, this thing must converge also. And those results are summarized by something called the direct comparison test. So the direct comparison test says that we have two series, a sub n, some of a sub n's and some of b sub n's, that are series with positive terms, and a sub n is always less than or equal to b sub n. Now, the first part of the theorem deals with convergence. If the series of b sub n's converge, then so does the sum from n equals 1 to a sub n. So what this says in words is that if a series with the larger terms converges, that means the smaller ones converge also. And the second part says if the smaller sum diverges, then the bigger sum has to also diverge. So if the sum with the smaller terms diverges, the bigger must also diverge. So here is the actual proof of this theorem. So what we have to remember is that a series is defined as a sequence of partial sums. So the first thing we're going to do is let the sequence S sub n be the partial sums for the series A sub n's, and we're going to let T sub n be the partial sums for the B sub n's. And let's just prove the first thing, which I'm going to call A. Okay, now the first thing we know is that since the series, so since both series have positive terms. We know that both the sequence of S sub n's and the sequence of T sub n's, both of these are increasing. So what you have to think about those S sub n's as T sub n's. So for example, with a number, S sub 5 would be the sum of the first 5 things. S sub 6 is the sum of the first 6 things. S sub 7 is the first 7 things. And because you keep adding on positive things as n increases, these sequences have to have terms that are increasing. So in A, you assume that the sum from n equals 1 to infinity of b sub n converges. So since the sum of b sub n's converge, we know that the T sub n terms go to some value b. And thus we have that because the terms of a sub n are smaller than b sub n, we have that s sub n is less than or equal to this value of b also. And this tells us then that the sequence of S sub n, the sequence of partial sums, is increasing and bounded, which means it converges. So that's proving the fact that if the larger series converges, the smaller one has to converge also. And that theorem that you use there is called the monotonic sequence theorem. Now, proving the second part is actually quite a bit simpler. So if the sum of a sub n's diverge, that means that the sequence of partial sums goes to infinity. But you have that the terms of the series of b sub n's are greater than a sub n's, so the partial sums T sub n is greater than S sub n, and thus your T sub n's also have to go to infinity, and that tells you that the sums of the B sub n's diverge. Now let's determine by direct comparison whether the following series converge or diverge. So this series, it looks an awful lot like 1 over 2 to the n, which converges. So notice that 5 plus 2 to the n is bigger than 2 to the n. So 1 over 5 plus 2 to the n is less than 1 over 2 to the n. And since that denominator is positive, this is also greater than 0. Now, since the sum from n equals 1 to infinity of 1 over 2 to the n converges, and that converges because it's a geometric series with r equal to 1/2. By direct comparison, the sum from n equals 1 to infinity of 1 over 5 plus 2 to the n also converges. So just think the terms, the series of the larger terms converges, so the smaller one must also converge. Determine whether the series converges or diverges by direct comparison. So you have the sum from n equals 3 to infinity of 1 over n minus 2. So this looks a lot like 1 over n, which we know diverges. So notice that n minus 2 is less than n. So 1 over n minus 2 is greater than 1 over n. And as the sum from n equals 3 to infinity of 1 over n diverges, that you can say that's either the harmonic series or it's a p series with p equal 1. A sum from n equals 3 to infinity 1 over n minus 2 also diverges by direct comparison. So why can't direct comparison be used to test the following series for convergence or divergence? So at least my suspicion with this first example is that this should diverge because comparing to the series from n equals 1 to infinity of 1 over root n, which is a p series with p equals 1/2, this is not that different, and maybe this should also diverge. However, if you try to set up your inequality, you know that 2 plus root n is greater than root n, so 1 over 2 plus root n is less than 1 over root n. So your series is smaller than a known divergent series, and you can't make any conclusion based on that. And similarly here, it feels like this should also converge by comparison to 1 over 2 to the n, but 2 to the n minus 1 is less than 2 to the n, so 1 over 2 to the n minus 1 is greater than 1 over 2 to the n, and so the series we want to make a conclusion about has terms that are larger than a known convergence series, and so we don't know if that's going to affect convergence or divergence. And in these situations, there's another test called the limit comparison test that you can use. So what the limit comparison test says is you have two series with positive terms, and if you take a limit of the ratio of their terms and it equals c, where c is a finite number and it's positive, then either both series converge or both diverge. And actually proving it is not super hard. So what we're going to do is let lowercase m and uppercase m be positive numbers, with that c value in between them. Okay? And since a sub n over b sub n approaches c for some very large value of n, so large capital N, if our little n is bigger than that capital N, we can guarantee that the terms, the a sub n's over b sub n's, are in between these values. So we have that as long as n is bigger than that capital N value, we have that a sub n over b sub n is in between little m and big M. And now you can multiply everything by b to the n, and the inequalities won't change because of the fact that b sub n's are positive. So we'll have m times b sub n is less than a sub n, which is less than capital M times b sub n. And now what we have is that if the sum of the b sub n's converge, so does the sum of capital M times b sub n, because that capital M can just factor out. And so by comparison, the sum of a sub n's converge. And similarly, if the sums of the a sub n's diverge, then so does the sum of m times little b sub n, which means that the b sub n's have to also diverge by the comparison test. So let's apply the limit comparison test to test this series for convergence or divergence. So first of all, just tell me what test you're using. So say you're using the limit comparison test. And we're going to compare to the sum from n equals 1 to infinity 1 over 3 to the n. And so I'm going to let a sub n equal the terms a sub n be 1 over 3 to the n minus 1, and b sub n equal 1 over 3 to the n. So now we'll find the limit as n goes to infinity of a sub n over b sub n. That's the limit as n goes to infinity, 1 over 3 to the n minus 1 over 1 over 3 to the n. I'm going to skip this step in the future, so pay attention. So what is always going to happen here when you have a fraction over a fraction is the denominator is going to reciprocate and become multiplication. You can think about it because you multiply by 3 to the n over 1, 3 to the n over 1, the denominators cancel out. So the denominator will always reciprocate, and in general I'm going to skip that step. So this equals the limit as n goes to infinity of 3 to the n over 3 to the n minus 1. Now we can divide the numerator and denominator by 3 to the n, and we'll have the limit as n goes to infinity of 1 over 1 minus 1 over 3 to the n, which is going to equal 1. And now, since we know that the sum from n equals 1 to infinity of 1 over 3 to the n converges, the sum from n equals 1 to infinity 1 over 3 to the n minus 1 also converges by the limit comparison test. The limit comparison test is especially useful when it might be hard to establish any kind of sort of inequality that would work for direct comparison. Like with this example, the sort of most important components here are the largest powers. So really we have n squared over n to the 5. So what I'm going to compare this to is the series from n equals 1 to infinity of 1 over n to the 3rd. And I know that converges because it's a p-series with p equal to 3. So let's let the a sub n's be the terms of the original series. So 2n squared minus 5 over 4n to the 5th plus n squared. And we'll let b sub n equal 1 over n cubed. Then we'll find the limit as n goes to infinity of a sub n over b sub n. So that will be 2n squared minus 5 over 4n to the 5th plus n squared multiplied by n cubed over 1. So now distribute. We have the limit as n goes to infinity of 2n to the 5th minus 5n cubed over 4n to the 5th plus n squared. Now if we divide the numerator and denominator by n to the 5th, we'll end up with 2 minus 5 over n squared over 4 plus 1 over n cubed, and that limit will be 1/2. And so thus, as the series from n equals 1 to infinity of 1 over n cubed converges, the sum from n equals 1 to infinity of 2n squared minus 5 over 4n to the 5th plus n squared also converges by the limit comparison test. Next, let's determine whether 9 to the n over 3 plus 10 to the n converges or diverges. think that direct comparison will also work here, but let's use the limit comparison test just to see how that works out. So ignoring that 3 in the bottom, it's awfully similar to 9 over 10 to the n, which is a convergent geometric series. So let's compare it to the sum from n equals 1 to infinity of 9 over 10 to the n. So we'll let a sub n be the terms of the original series, 9 to the n over 3 plus 10 to the n, and the terms of bn be 9 to the n over 10 to the n. And then we'll find a limit as n goes to infinity of a sub n over b sub n. So that's 9 to the n over 3 plus 10 to the n, multiplied by 10 to the n over 9 to the n. Multiplying 9 to the n by 10 to the n gives us 90 to the n over 3 times 9 to the n plus 90 to the n. Now if we divide by 90 to the n, we'll have the limit as n goes to infinity of 1 over 3 times 90. 9 over 90 will be 1/10 to the n plus 1. And multiplying 1/10 by itself repeatedly as n goes to infinity is going to give us 0. So this limit is equal to 1. And so by the limit comparison test, as the series from n equals 1 to infinity of 9 to the n over 10 to the n, note that's the same thing as n equals 1 to infinity of 9/10 to the n. As that converges, so must our series. So must the sum from n equals 1 to infinity of 9 to the n over 3 plus 10 to the n. So one thing you'll notice in this section and the previous section, the answer is whether it converges or diverges, but it's also very important to explain why you can come to that why you can make that conclusion. All right, next. So in determining what to compare the terms of this series to, I think that it's best to take that denominator and expand it out. So if you do so, let's let those terms be a sub n. The numerator is 5 plus 2n. When you expand 1 plus n squared, that quantity squared, we'll get n to the 4th plus 2n squared plus 1. And so the most important term in the numerator is the 2n. Denominator is n to the 4th. So comparing this with something that's n over n to the 4th or 1 over n cubed, we'll use those for our b sub n's. So let's find the limit as n goes to infinity of a sub n over b sub n. So 5 plus 2n over n to the 4th plus 2n squared plus 1 multiplied by n cubed over 1. So that will give us the limit as n goes to infinity of 5n cubed plus 2n to the 4th over n to the 4th plus 2n squared plus 1. And we will divide the numerator and denominator by n to the 4th. So 5 over n plus 2 over 1 plus 2 over n squared plus 1 over n to the 4th. And that limit will equal 2. And so, thus, as the series from n equals 1 to infinity of 1 over n cubed converges, it's a p series with p equal to 3, we have that the sum from n equals 1 to infinity of 5 plus 2n over 1 plus 1 plus n squared, the quantity squared, converges by the limit comparison test. So in the next example, it's a little bit trickier because you have something involving a root. So when determining what to compare to, the dominant power in the numerator is the n squared, and the denominator is n to the sixth. But that n to the sixth is rooted, so the root of n to the sixth is n to the third. So that suggests that what you should compare this to is n squared over that. So n squared over n to the sixth, or n squared over n to the third, which will be 1 over n. So just be aware that the root is also a power, and that is going to influence what you decide to compare the terms of your series to. So let's let the terms a sub n be 1 plus n squared all over the root of 1 plus n squared plus n to the sixth, and b sub n equal 1 over n. If we find the limit as n goes to infinity of a sub n over b sub n, that'll be the limit as n goes to infinity, 1 plus n squared over the root 1 plus n squared plus n sixth multiplied by n over 1, or the limit as n goes to infinity of n plus n squared plus n cubed over the root of 1 plus n squared plus n to the sixth. Now I'm going to divide the numerator by n to the third, and the denominator also, but when that n to the third goes inside of the square root, it gets squared and becomes n to the sixth. So in the numerator, what we have is the following. We have 1 over n squared plus 1 over n plus 1. And the denominator, that n cubed becomes n to the sixth when it goes inside the root, and we have the root of 1 over n to the sixth plus 1 over n to the fourth plus 1. And this limit is equal to 1. So that tells us as the sum from n equals 1 to infinity of 1 over n diverges by the limit comparison test, the sum from n equals 1 to infinity of 1 plus n squared over root 1 plus n squared plus n to the sixth also diverges. Now next, in the final example, we're sort of mixing up n's as coefficients and n's in powers, but just think for a second, if that minus 1 wasn't there, those n's could cancel and you just have 1 over 4 to the n, which would converge. So we're going to apply the limit comparison test. With a sub n equaling the terms of our series, and then b sub n just equaling 4 to the n. So we'll find the limit as n goes to infinity of a sub n over b sub n. So that'll be n minus 1 over n times 4 to the n times 4 to the n over 1. And those 4 to the n's can cancel, and we'll have the limit as n goes to infinity of n minus 1 over n, which is the same thing as the limit as n goes to infinity of 1 minus 1 over n, which will equal 1. And now we know as the sum from n equals 1 to infinity of 1 over 4 to the n converges. It's a geometric series with r equal to 1/4. The sum from n equals 1 to infinity of n minus 1 over n times 4 to the n also converges by the limit comparison test.